So we spent a lot of time talking about the expectation, or the expected value, of a random variable, which is supposed to be interpreted as the sort of center, or average, value. And now we're going to switch to talking about, whoopsies, oh my goodness, a measure of the spread of a random variable, which we call the variance. So let's define that. Variance of a random variable x is denoted v of x, and it is defined to be, we will write this down and then take a minute to unwind it. So the expected value of x minus expected value of x squared. You can write this as sum over s in s of x of s minus expected value of x squared times the probability of s. So, what does this mean? So, one quick note, let me change this a little bit and write mu, this is the Greek letter mu, for the expected value of x. This is a common letter to use for this. And that will just clean this up a little bit. We can erase this guy here and replace it with mu. And maybe that makes it a little more clear what's going on. So what's going on is basically how spread out is this random variable. We're measuring that by measuring the average distance between an outcome, which is measured by our random variable x, and the average outcome measured by the expected value mu. So this thing is a constant. Mu is just some number. It's the expected value. And x is our random variable. So this formula here is taking the expected value, which is sort of an average, of the distance between an outcome and the average outcome. So how far are the outcomes from the average is what this is generally measuring. And the square does not have a big intuitive significance, but it basically adds to the sort of weighting. You know, it's in the same spirit as doing linear regression using sums of squares, things like that. In statistics and probability, you often square things just because of the way it affects the weighting. And then what is this side? So first of all, it's just the definition of expected value. This is what you get when you write out the expected value of this is that summed over outcomes times the probability of each outcome. And again, you can see that we're sort of taking a weighted average over the distance between an outcome and the expected value. So that is what variance is, and that is why it's measuring the sort of spread of a random variable. And there is a very closely related measure called the standard deviation, which is sigma of x, which is the square root of the variance. So again, this is a common thing that you'll see in probability and statistics, is to take some kind of average of squares and then take the square root. And this just gives, you know, a slightly different scaling of your measurement. So we will see many examples of these things, but first I want to give an alternative definition because it is almost always what you will use in practice. So let's, I'm saying it's an alternative definition, but let's call it a theorem. The variance of x is equal to the expected value of x squared minus the expected value of x squared. So let's take a second to unwind this a little bit. The big difference, so these, do not get these confused. The big difference is that here, the square is inside the expectation, and here, the square is outside the expectation. And that will make a difference, as we will see. In particular, this thing is always bigger or equal to this thing. So the variance is always going to be positive, as you expect from this formula, because you're taking an average of square things, which are always positive. Positive or zero. So let's prove this. This one is, we've seen a couple of proofs about expected value that basically boil down to rearranging the sum. And this is going to be similar, kind of just rearranging the sum. Basically, we have to expand this square, we're going to expand out this square in the definition of variation, and we'll see that this is sort of what falls out from that. So let's do that. So we're essentially expanding the square. So the variation of x is defined to be the sum over s in s of random variable at s minus the expected value of random variable, a constant, squared times the probability of s. This is exactly the definition that we wrote down up here. And now, like I said, we're going to expand this square. And what we get, so I'm going to write it out as separate summations. In fact, let me not do that. So I'm just going to expand it out in place. We're going to get x of s squared minus 2x of s expected value of x plus expected value of x squared. And now the point is that we can give each of these terms its own summation. So basically, we're going to distribute this term into each part and then write out the sums separately. So when we do that, we get the sum over s in s of x of s squared times the probability of s minus 2. So this guy, which is going to appear in this term in the sum, this is a constant, so we can just factor it out the front. And what we are left with is x of s, probability of s. And in the last term, this whole thing is a constant, so we can factor it all out. And what we get is this. And now to conclude, well, we essentially just have to recognize that this thing is the expected value of the random variable x squared. Because you can see we are taking the weighted average of the values of x squared at every possible outcome. So that's what this is. This thing, this summation right here, is the weighted average of x. So this is just the expected value of x. And this thing is just the sum of all the probabilities of all the outcomes, which must total to 1. So rewriting this, we get expected value of x squared minus 2 expected value of x times expected value of x. So that's the square outside, plus 1 times expected value of x squared, and this just cancels with this to give expected value of x squared minus expected value of x squared. And that is the formula that we were aiming for. Wonderful. So let's go ahead and do some examples. And again, we're usually going to use this formula when we're computing things because, you know, it's a better formula to work with in general. So, for example, what is the variance of x, a random variable, which is a 6-sided die? So again, meaning x is uniformly distributed on the outcomes 1 through 6. So let's rewrite this formula just to have it always in mind. So we just need to compute these two things. And we've seen before that the expected value of x is 3.5, or 7/2. So we need to compute the expected value of x squared. What is that? Well, x squared is basically the same as x, except you square all the outcomes. So x was uniform on the set 1 through 6. So x squared is uniform on 1 squared through 6 squared. So the expected value of x is just the, since it's uniform, it's the literal average rather than some kind of weighted average. And if you multiply this out, it turns out to be 91/6. So the variance now we can compute is, oopsies, we should have a little square in there. So the expected value of x squared. So the variance is expected value of x squared minus expected value of x squared on the outside, which in this case is 91/6 from here, minus 7/2 squared. And if you work this out, this turns out to be 35/12, which is about 2.9. So the expected value, on the one hand, which is measuring the center of the distribution, is fairly easy to interpret because it is a number that should lie basically at the center of this distribution in some sense. The variance has a good interpretation in terms of measuring the spread, but it's a little bit harder to give specific interpretations to specific numbers. So it's more about getting a feel for what kind of things mean from examples. So for example, a uniform distribution on 1 through 6, as in this example, has a variation of about 3. So somehow you could imagine that to mean that it's telling you that the sort of radius of this distribution is about 3, but it's not going to be quite that clear-cut. But you can try to develop some kind of intuition like that if you do a lot of examples. But actually, let's dig a little bit deeper, and maybe we can say a little bit more about this. So in general, if x is uniformly distributed on the set 1 through n, then I'm not going to do this out, but here is maybe a good practice problem for you. The variance of x is n squared minus 1 over 12. As we saw in this case, when x is uniformly distributed on 1 through 6, so n equals 6, this is indeed n squared minus 1 over 12. So that checks out. And what this is telling us is that the fact that the radius here is about the same as the variance is kind of a coincidence in this case. That's not going to be a general pattern, because you can see that from our general formula, as you increase the width of this distribution, the variance actually is increasing as the square of this width. But in particular, this is one of the reasons why sometimes you're interested in the variance and sometimes you're interested in the standard deviation. The standard deviation maybe gives a more reasonable measurement of how wide this distribution is, because since it's the square root, this is going to increase linearly with n. So the standard deviation is going to do a better, is going to track more closely the width of this distribution in a linear way. Excellent. Let's do one more example. Let's calculate the variance of a Bernoulli trial with success probability p. So let's call this, let me real quick make some room for this. So let's call this x. X is our Bernoulli trial with success probability p. So remember that this means x takes the values 0 or 1, and the probability of 0 is 1 minus p, and the probability of 1 is p. So recall the expected value, we're going to need to know this, and I believe we've computed this before, but if we haven't, you can just do it in your head. It's 0 times 1 minus p plus 1 times p. So it's just p. And now to compute the expected value of x squared, since x only takes the values 0 and 1, like we said earlier, x squared is going to be the same distribution, except that we square every value. And these things square to themselves. 0 squared is 0, 1 squared is 1. So x squared is just equal to x. So the expected value of x squared is the same as the expected value of x, which is, again, p. And then we can compute the variance. It is the expected value of x squared minus the expected value of x squared, which is this thing we have said is p, and this thing we have said is p, so it's minus p squared. And it's nice to write this as p times 1 minus p, because often you can imagine a Bernoulli trial as having two parameters, p and 1 minus p. These are the two probabilities. And so the variance is just the product of those two things. It's a very clean formula. And as a bit of intuition in this situation, this is largest when p is equal to 1/2. Then the variance p times 1 minus p is just 1/2 times 1/2, which is 1/4. Write that, so variance is 1/4. And this should sort of match some kind of intuition. That the p equals 1/2 case is somehow the most random. Because, for example, if p is bigger than 1/2, then you can expect to see heads, maybe more often than tails. And if p is less than 1/2, you can expect to see tails, or failures, I guess, more often than heads or successes. But when p is equal to 1/2, this is the most random situation because you don't really have any expectation one way or the other. So this is some intuition for why the variation should be the largest when p is equal to 1/2. And it also shows that it's not exactly measuring the width of the distribution or the spread of the outcomes, because in all cases, a Bernoulli random variable, a Bernoulli trial, only has 2 outcomes, 0 and 1. But as we're seeing, the variation will change depending on the probabilities of those outcomes. So there is that subtlety as well.